All right, so the first thing we're going to talk about today is a Calc 1 concept, chain rule. Now, we alluded to it when we're taking derivatives and things are really simple. If z is a function of x and y, and I'm taking partial derivatives, I know when to use a chain rule, right? Because maybe I have a composition of functions. But now it's really the more detailed version of the chain rule. For example, if y equals x of t, okay? Or I should say, yeah, y, and I want to find dy dx. I want to find dy dt. These are two different things. So if you remember from Calc 1, there's a chain rule going on here. I want to find the derivative, so I kind of go outside in, right? Kind of work my way in. One of my favorite types of problems was, you're blowing up the balloon at a constant rate. How fast is the volume changing? Blah, 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 blah. And people will write things like, v prime equals. Well, I fortunately had an instructor who basically said anybody who ever uses prime on a variable clearly has no idea what they're doing. And if somebody's teaching with prime on a variable, they should be removed from the classroom because there's no such mathematics of putting a prime on a variable. You can only put a prime on a function. That's it. Prime on a variable. I want to make sure you guys understand this. This has two possible values. It can only be 0 or 1. There is nothing else you could write that would make any sense mathematically. Why? Because if I'm differentiating with respect to x, it's 1. With any other variable, it's 0. Because now you know about partial derivatives. There's no such thing as variable prime, quantity prime. I have people that write everything prime in this class. I actually have no idea what the intent is when someone puts a prime. I'll say, give me the derivatives. All right, so I have xy cubed prime. I'm actually getting people turning in stuff like this. I'm a mathematician. I've helped edit multiple math books. My name's in half the math books you'll have at Mesa College, and I have no idea what this means mathematically. I throw up my hands saying, there's no such thing, and anything you write, I'm really excited to see what comes next, because that has no meaning mathematically. There's an infinite number of things I can take the derivative with respect to. I can take the derivative with respect to x, y, or any other variable that exists, by the way. And now that you know partial derivatives, x and y might be a function of that other variable, or it might not be. And if it's not, then it's 0. If it is, then it's... So you always want to be very specific on your notation. So let's start with something like this. I've got z equals f of xy. But x is actually a function of t, and y is a function of t. I'm going to be really generic in general. I can ask for the derivative of z with respect to x. I can ask for the derivative of z with respect to y. Or I can ask for the derivative of z with respect to t, can't I? Now, part of the process is knowing when am I doing ordinary derivatives and when am I doing partial derivatives. How many variables does z see? Z sees 2. So any derivative of z is partial. Does that make sense? How many variables does x see? 1. So any derivative of x would be ordinary. Okay? So I would like the derivative of z with respect to t. I'm going to leave the d out for a moment. So that means I'm going to differentiate z with respect to x, and then differentiate x with respect to t. But I could also differentiate the y. Plus, and we saw an example of this last day when we were doing the differentials, the tangent plane estimations. I add the other derivative. Now let's make it easy. We just said a moment ago that x and y only see one variable. They only see t. So these derivatives are ordinary. That means straight up and down d's. Z sees 2 variables. So any derivative of z we said was going to be a partial derivative. Now, I'm going to give you a simple illustration, and there's a few versions of this that we're going to learn. This is actually what's taking place. Right? Z sees x and y, but x and y ultimately are both functions of t. Does that mean my original statement, could I have written as z is a function of t and t alone? Think about that for a moment. So your head's nodding, head's shaking, head's going the diagonal. That's take it either way. So what if I said z was x squared y? X is sine t and y is t cubed. Then technically, couldn't I say that z is sine squared times t cubed? So that's what I'm saying. Ultimately, isn't z a function of t and t only? So therefore, ordinary or partial? This one here. Ordinary. And my picture kind of illustrates it. Ultimately, there's only one independent variable. X and y are both technically functions. They're both dependent variables. So z with respect to x or with respect to y are partials. X and y with respect to t are ordinary. So ultimately, z was ordinary. And here's the picture that kind of illustrates that. So if I wanted to do a problem like this, let's do this one. Erase this for a moment. I want to take the derivative dz dt. So that's the partial of c with respect to x. What's the partial with respect to x? Two xy times the derivative of x with respect to t, which would be cosine t. Now the derivative of y with, the z with respect to y would be partial of z with respect to y? X squared. X squared, and then the partial of, or the derivative of y with respect to t? Now, I hate this answer. Why? It's correct. Why do we hate this answer so far? Too many what? Variables. Shouldn't my answer be a function of t and t alone? Oh, so what should I do at this point? Substitute. So this would then be 2 sine t times t cubed times cos t plus sine squared t times 3t squared. If we had simply made that substitution in the beginning, we said z was going to be sine squared t times t cubed. Now if I use product rule on this from Calc 1, first times derivative of the second, second times derivative of the first, we get the same answer. This is kind of the justification that what we did was correct. Now, in general, if this were the situation, substituting before you start would probably make more sense, but a lot of times that's not going to be part of the problem. It's not going to be necessary, But we saw that validated this. Awesome. All right, this is the first example. Now let's try something else. Let's do a different what if. All right, how about w equals a function of z, and z is a function of x and y. Now this one's a little bit trickier. So I always like drawing a picture to make this illustration so much easier. How many variables does w see? One. W sees z and z alone. But how many variables does z see? Two. There's my simple illustration. So ultimately, you always want to take derivatives of the innermost variables. That's how this always works. You never take a derivative of the outer one only. So w can take a derivative with respect to x or with respect to y. So I want the derivative of w with respect to x. What do you think that's going to be? It's going to have to be the derivative of w with respect to z, and then the derivative of z with respect to x. Do you agree? Now, are they both ordinary? Are they both partial? Is one ordinary and one partial? What do you think? What do you think?
One's ordinary, one's partial.
So which one's which?
The first one's ordinary.
The first one's ordinary because?
It only sees each.
Exactly, that's it. It's actually that simple. W sees only one variable, so W's derivative has to be ordinary. Now, Z sees two variables, X and Y. Okay, so, whoops, I'm sorry, I put the I put the D in the wrong place. Sorry, we're here still. That's the D. So this would have to be partial because Z sees 2. Now let's go back to the original question. W had 2 choices, X or Y. So therefore, would this one be ordinary or partial?
Partial.
Ultimately, this was partial because at the end of the line, there were 2 choices. And then if I did the derivative with respect to Y, it would look very similar. Okay? We do one more example, and this is one of the most common ones. Think polar coordinates for a moment, because polar coordinates are going to be huge in a few weeks. A lot of folks think polar and go, oh no, oh, polar is so hard. Actually, polar is going to be your favorite thing to do, because the absolute rule of thumb is if you have to go polar, it's because rectangular is too difficult to work with, and polar probably made it really, really easy. That's pretty much always the case. Anytime you're going polar, you're taking something extremely difficult and making it extremely easy. There's no problem that exists where you go easy to hard, because you wouldn't switch it if it made it hard. You'd switch it only because it makes it easy. But it makes derivatives kind of interesting, because each variable is a function of 2 more variables. So I'll just sort of loosely say W is a function of X and Y, but X is a function of, we'll use R and theta. And Y is also a function of R and theta. I'm in the XY plane and I want to convert it to polar. So both X and Y, right, will have to be manipulated. This one is very tricky now, isn't it? So what does my picture now look like? W has 2 choices. X has 2 choices. I can't get from here to here. No, X here, Y here. So ultimately, W can be differentiated with respect to R or with respect to theta, can't it? And this is going to turn out to be a fairly common one. So my original variable was a function of 2 variables, and each of those was a function of 2 variables. We could do 3 variables, we could do 10. Once you have 2, the rules will be the same for 2 or more. In other words, function of 1 variable, it's ordinary, 2 or more is partial. So we don't need 10 variables here, it's the same thing. I want to take the derivative of W with respect to R. Okay? But there's 2 different ways to get to R. I can get to R this way, I can get to R this way. So I'm going to do both of them and they get added. So that means I'm going to have to differentiate W with respect to X and then differentiate X with respect to R. And to that I will add W with respect to Y and then Y with respect to R. So now, I'm not worried about the first one. W has 2 choices. So both derivatives of W with respect to X and with respect to Y have to be partials. Okay? X has 2 choices, R and theta. So the derivative of X with respect to R has to be partial. Y has 2 choices, R and theta. So this one has to be partial. Now, ultimately, W, there were 2 variables ultimately, R and theta. Partial or ordinary?
Partial.
Partial, because again, the 2 at the end. So this one was all partial derivatives. The rule of thumb, it's only going to be ordinary. Think embedded parentheses, right? F is a function of G is a function of H, however many you want. When you go to that next set of parentheses, how many variables do you see? If you only see 1, then that derivative is ordinary, even if the next one is partial. Now, the final answer is partial because at the end of the line, there are still 2 variables at the end. Just for the heck of it. What if we decide to go crazy here and say, and now R and theta are both functions of T, just for fun. What if we did one more step here and we said R is actually a function of T and theta is a function of T? What if we did that? Then wouldn't it look like this? I would still add. But now W with the derivative of W with respect to T would be ordinary, wouldn't it? And dr dt would be ordinary. And dr dt would go right here and right here. You could do this on and on and on and on. You can. How many variables does that person see? Or does that variable see? That's it. Those are the rules. And so we're going to manipulate that And one of my favorite ways of manipulating this is to take everybody's favorite differentiation form from Calc 1. Do you remember your favorite type of derivative in Calc 1? I'm winking with my left eye. Remember implicit differentiation? Oh God, you hated it. Yeah, there's never been a calc student who's ever lived in the history of the world who said, oh boy, implicit differentiation. Oh God, it's the worst thing ever. Because it's confusing, it's difficult, but it's actually how most differentiation is actually done. People don't realize that. Not everything is an explicitly defined function. So if I want derivatives of things that aren't explicitly defined, I have to have a way of doing it. So I'm going to go back and review a little bit of implicit so that we can then tweak it, okay? So let me start with one of my favorite examples. Take a simple circle of radius r centered at the origin. In this case, r is a constant, okay? Okay, the problem with circles in general, I mean, circles are very important, right? Really hugely helpful shapes, but they're not functions. And we know in calculus, anything that's not a function tends to be harder to work with because differentiation is not trivial. So, I want to take the derivative. Well, one thing I can do is I can think of this as top half, bottom half. If I asked you to graph this circle on your graphing calculator, just straight up, could you do it? Is there a graphing calculator that exists that will graph that? No. So what do? You learned probably as high school students. How do you graph the circle? It's easy. You do top half and bottom half as two functions. That's it. There is no other way. It's trivial. You go, oh, I just do top half, bottom half, and graph two functions, and then you get a circle. Can you do that with hyperbolas and ellipses? Sure. No one ever thinks of those. But everyone knows in circles, if I go top half, bottom half, that'll work. So let's look at the top half. The top half would be y equals x squared plus y, not x squared, sorry. Y equals r squared minus x squared to the 1/2 power. That's the top half, right? The bottom half would be what? Y equals the negative of that. I'm going to put it as 1/2 because it makes the derivative a lot easier if I do that, as we know. I lost my caps. Ah.
It's right in front of the...
I have a good pen, I don't want to lose it. Ugh. Okay. Okay, so let's do both halves. Again, we've all done this before. Hopefully you did this in Calc 1. I do this in about, I don't know, day 5 or 6 of Calc 1. So dy dx is 1/2 r squared minus x squared to the negative 1/2, and then the chain rule factor is negative 2x. Remember, r is a constant. Okay? And if I simplify that, which I should, it makes it a lot easier, that simplifies to negative x over the square root of r squared minus x squared. Which, by the way, is simply negative x over y, isn't it? And by the way, that is actually very useful to write it in that form. Now, how about the bottom half? dy dx is negative 1/2 r squared minus x squared to the negative 1/2, and then same chain rule. And now when I simplify that, the negatives cancel beautifully.
Okay, thank you.
Except I don't want to cancel the negatives. I'm going to still leave that negative, I'm going to leave that negative, and I'm going to leave that negative. Everyone see that? These are opposite signs because why would I do that? Because it's still negative x over y, isn't it? Oh, so if I differentiate the top half, it is negative x over y. If I differentiate the bottom half, it is negative x over y. That's a good thing. Now let's differentiate it implicitly, to remind ourselves of how that process works, because that's way easier, way faster, way more efficient. So I have x squared plus y squared equals r squared, and I want to differentiate both sides with respect to x. Now, The very statement in Calc 1, this is an absolute, this unyielding statement. There can only be one independent variable. Therefore, every other variable that exists, you can just make up as many letters of the alphabet as you want. Every other variable that exists has to be a function of the one independent variable. There is no exception because there can only be one. So if I wrote 100 variables up there, they're all functions of x. How do I know that? That's what d dx means. It says ordinary derivative with respect to x because there is no other independent variable. That's why the capital D's are so, or excuse me, the vertical D's are so important. That statement, the d dx says there is exactly one independent variable, therefore every other variable is a function of that variable. Period. There's no exception. It changes in Calc 3 because we are allowed to have multiple independent variables. That's why we use different notation, and that's why our chain rules are a little bit busier. So when I differentiate this, the derivative of x squared, that's 2x. But when you see y squared, you don't see variable squared, you see function of x squared. All right? Because otherwise you're only going to write 2y, which would be incorrect in every context. The derivative of y squared is not 2y. The derivative of y squared is what? 2y times the derivative of y with respect to x. That's called the chain rule factor. Now, if you wrote y of x all the way through, sometimes it's easier to remember, but most of us don't. We just have to remember this. And then what's the right side? 0, because r is a constant. Now, let's gather terms. So 2y dy dx equals negative 2x. Therefore, dy dx is negative x over y. Oh my gosh. Same answer we got before. Well, yeah, we're supposed to get the same answer. But algebraically, it is way faster if I do it correctly. Now, there's one more way of doing this that's kind of interesting. There's the geometric. What is the slope of this?
Over x.
This slope would be y over x. Everybody agree with that? What do we know about a tangent line of a circle and the point of tangency on the circle? What do we know about these?
Orthogonal.
They're orthogonal. And the reason we know it's orthogonal is the easiest way of saying it is the shortest distance from the line to the circle has to be the perpendicular distance. Oh, okay, and what do we know about perpendiculars? What's the slope of the perpendicular? Isn't it? Oh, man, I could have done this whole thing geometrically. Yeah, but the nice thing is we just found this 3 different ways. Geometrically, the long way, and implicitly. But it's implicit that's the important one. Because in general, you can't always do things geometrically. You don't always have a picture in front of you. You know, the pictures sometimes are too difficult because you couldn't solve explicitly for the variable in question. But we know this is true. Now, with this in mind, okay, let's take a slightly more complicated version. Because I want to do 2 different forms of implicit. I want to do one with 1 independent variable and one with 2. Just to walk you through the process. Because it can be kind of gnarly. All right, so let's start with I want to make it 2 more. I've got 3x squared y cubed minus the sine of xy equals, how about, I don't know, something evil. How about e to the y? That's pretty terrible. And the instruction is to find dy dx. So the statement dy dx means that all of my y's are functions of x, but I cannot solve explicitly. In the equation of a circle, you cannot solve explicitly for y, because you'd get a plus or minus. That's not a function. But by assuming all the y's are functions of x, it allows me to use calculus and derivative and find slopes of tangent lines and things like that, and I get consistency. It's not possible to write y equals. Let's suppose this is just the most hideous evil curve imaginable. You know, it's a figure 8 with, you know, all sorts of weird stuff going on. But even in a figure 8, you know, that's, to me, it's like the most evil shape, a figure 8. Can't I still ask for the slope of the tangent line at any given point that isn't vertical? Yeah. There's nothing wrong with asking the question, what's the slope of the tangent line? The problem is I can't solve explicitly for y and take a simple derivative. So we have to differentiate both sides, gather dy dx terms, and then that's it. So, let's do it. So in the first case, the derivative with respect to x, that's a product. I have to treat it as a product rule. Yikes. It's going to be first times derivative of second plus the second times the derivative of the first. Well, that'd just be a 6x. That's easy. Now the next one. The derivative of minus sine of thing would be minus cosine of thing. And now I have to differentiate xy. Ugh. So how do I differentiate xy? First times the derivative of the second plus the second times the derivative of the first. All right, I'm done with the left side. Derivative of e to the y? E to the y times dy dx. If I am missing even one dy dx, it will have a pretty huge impact on the answer. Now, here's the best part of implicit though. The dy dx terms will always stand alone as multiplications. So all I have to do is gather all the terms that have dy dx's and then factor it out. The algebra from this point on is actually pretty low level. It's getting to this point. So probably I should distribute here. So what would that be? Or in fact, let me clean each one of these up. So this one here is going to be 9x squared y squared dy dx plus 6xy cubed minus x cosine xy dy dx minus y cosine xy equals e to the y dy dx. Wow, that's very busy, isn't it? Very busy. Okay, but getting the dy dx's now is an easy thing. So I'm gonna, let's see, I already have a couple here, so I'm gonna move this guy this way, I'm gonna send this guy this way, and I'm gonna send this guy this way. I do this so I don't lose them. So I have a dy dx term, a dy dx term, and I'll have this dy dx term on the left. I'll have these two terms on the right. Okay, so I will have 9x squared y squared minus x cosine xy minus e to the y dy dx. On the right-hand side, I will have negative 6xy cubed plus y cosine xy. Does that look right? Now writing my final answer will be easy, because my final answer is just going to be a quotient now. So the final answer is, I'll put it up here, I need the space. Dy dx is this over this. Yikes. Right? This is Calc 1. We learned how to do this in Calc 1. We didn't love it, but that's it. It's the only way we know how to get that answered. A lot of work, though. Okay? Boy, wouldn't it be great if there was an easier way? Right eye wink. You know there is an easier way. See, left eye wink, I'm deceiving you.
You always look for the right eye.
Okay. Now I want to do a similar problem, because then we're going to come back to both of these. Now, let's suppose I have something like this. I've got, I want to keep it fairly small. I've got x squared z plus about tan z equals yz squared. Okay, something icky like this. And we're going to assume that y is, or excuse me, that z is a function of x and y. We're going to assume that z is a function of x and y. Okay? Well, actually, let me throw in one more thing. Sorry. Let me throw in y squared z. There we go. Make it a little more interesting. I want the derivative of z with respect to x, or I want the derivative of z with respect to y. It doesn't matter which one I ask. In this case, I think the derivative with respect to y will be more interesting. So I want to find the partial of z with respect to y. Yikes. So what we're assuming now is that x and y are independent variables, and z is a function of both x and y. Problem is, I cannot write z equals, like before. I can't isolate the dependent variable. So we will do implicit differentiation on this thing. So we'll go slow. So x and y are independent, so I'm differentiating with respect to y. So basically, this is what I'm doing. I'm doing the partial with respect to y of both sides. Got it? That's what we're doing. So, in the first case, the derivative with respect to y, but z is also a function of y, so there will be a product rule. What do I do with the x squared?
Constant.
Treat it as a constant. So let's go first times derivative of second, so that'd be x squared y squared times the derivative of the z, plus the second times the derivative of the first. So that would be x squared z times 2y. That's straight up product rule. You notice the x squared just went along for the ride. It was treated as a constant. So if you ignored the x squared, y squared times the derivative of z, boom. Z times the derivative of y squared, boom. And then the x squared was just a constant. What is the derivative of the tangent of thing? Secant squared of thing times the derivative of thing. That's the chain rule. That's why I like using the formal notation, thing. And then the last term, first times derivative of second, plus the second times the derivative of the first. And I don't think this was any worse than the first example we did. So now it's the same thing. Gather the dz, dy terms. All right, how many do I have here? I've got this one. I'm going to move to the left. I'm going to move this guy to the right. And I think that's all the movement I need to do. All right, so I'm going to have x squared y squared plus secant squared minus 2yz all times the partial. On the right side, I will have the negative of this, and don't want to lose that, 2x squared yz plus z squared. I think I got that right. So now, when I write my final answer, the partial of z with respect to y is this over this. All right, whew, that was busy. Now, what we may not have realized before, that implicit differentiation is the way of the world, no matter how many variables you have. If you cannot isolate the dependent variable, then you have to differentiate both sides and gather terms, which means that's what you're doing. You're doing implicit differentiation. But boy, both of these processes are kind of long. So what if we look at it from a different point of view? I mentioned to you before that anything in 2 dimensions is a slice of something in 3. We know this. In fact, we've actually used this to our advantage already a couple times. So what if I took something as simple as, let's suppose I have something as simple as, I have y equals f of x. I have this. We know that if I wrote y minus f of x or f of x minus y, then that would equal 0, which would be a slice of something. We call that a level curve. But then I could set it equal to any value, right? Our circular paraboloid, we know that. I'll use the simplest example I can think of. X squared plus y squared equals r squared. If I say, I want to make this into a new function, I'm going to call it f of xy equals x squared plus y squared minus r squared. I'm not going to say equals 0, Because if I say equals 0, then I'm saying f of xy is always 0. No, 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 no. If f of xy equals 0, I get this particular two-dimensional curve back. But the graph of this thing, this is way cooler than that. Right? This is a circular paraboloid. What makes this one particularly interesting is that one there, when z equals 0, is this. This is a slice of this. But I don't want to set my function equal to 0. I just want to know that this particular curve is a slice of this, but I want to work with this. This is way easier to work with in general. Why? Because this is a function. I can take derivatives. I can do things that I can't do with this one easily. So if I start with something like this, suppose I then said, okay, let's, which one do I want to use? I want to use, well, actually it doesn't really matter. I want to call this f of xy, capital F, okay? And the one I want to use is, actually it doesn't matter. I'm just going to say it's going to be the difference, okay? Sorry. So if I take capital of fxy, which of course is equal to 0, I'm just going to put things on the same side, equals 0. That's going to be one specific curve, but I want that one. I want to differentiate this one specifically. So I do want to set this one equal to 0 and then differentiate it in a sense. So if I differentiate this, I want to do it with respect to both x and y. Okay? So if I do that, okay, let's see. Here's how I want you to think of that. I want you to think of y as a function of x. Again, in the sense of implicit differentiation, it only worked if I thought of y as a function of x, not as a separate variable. So in a sense, think of this as f of x comma y of x. So that means there's one independent variable, but I'm treating this as two variables. But the one independent variable, of course, would be x. So let's differentiate with respect to x. Okay, according to my chain rule, okay, let's do this if it makes it easier. Because sometimes when we were doing that for the variable's sake, right? So let z equal f of xy or something like that. I want to differentiate both sides with respect to x. So that means I want to differentiate dw dx. So that will be the partial of f with respect to x, which I'll write like that, times d dx of x. That's kind of redundant. That's 1. Plus the partial of f with respect to y times d dx of y. Just using formal notation here. All right? Well, what is the left or the right side at the moment? It's the partial of f with respect to x times what? What's the derivative of x with respect to x?
1.
1. Oh, okay. What's the derivative of y with respect to x? Well, that's dy dx. Okay. But didn't I just differentiate 0? So what's the derivative of w with respect to x if w is actually equal to 0?
0.
Huh. My goal was to find dy dx in general. Can I just manipulate this, move things around? What if I move this guy this way? Then wouldn't that mean that dy dx is the negative of the partial with respect to x over the partial with respect to y? Huh. I wonder. Did we just find a shortcut? Let's check this out. Let's take this really, really nasty problem we started with over here. Okay? I'm going to erase. This is the result we got. I'm going to erase because I want to. Actually, I'll do it over here. So let's go back to the original problem, which was 3x squared y minus the sine of xy equals e to the y. All I need to do is get everything on the same side so this equals 0. So I'm going to say, let's let capital F of xy equal 3x squared y minus the sine of xy, then what? Minus e to the y. I need everything on the same side so it equals 0. Now I have some function of two variables. Now I have a three-dimensional problem, but when this is 0, it's exactly this, isn't it? This is the level curve that this produces when it's 0. But I don't need this to be 0 to take a derivative. So, I just took the original problem, put everything on the same side, and that's my starting point. But here's what I need to do. I need to find these two quantities. The key first step is get everything on the same side. Otherwise, your final answer, you're going to have wrong signs.
And then put the y cubed.
Did I lose something? Oh, thank you. I can't see that far. Does that look right? Y cubed. Okay, let's take the partial with respect to x. And what would we get? 6x y cubed. With respect to x, it'd be minus cosine of xy times derivative, which would be y, and that would be 0. Okay? Let's take the derivative of this with respect to y.
9.
Oh, I'm sorry. I don't want to put that 3 there, do I? So 9, what?
X squared y squared.
X squared y squared minus cosine xy
X.
times x. What about this guy?
Minus e to the y.
Minus e to the y. Because we're treating x and y as independent variables for what we're doing right now, there's no chain rule factors. Again, anything in 2 dimensions can be considered a slice of something in 3, making all variables independent variables. Now, according to this crazy formula we just derived, the answer to the question dy dx is supposed to be the negative of fx, it's supposed to be the negative of this, okay? Over that, which would be 9x squared y squared minus x cosine xy minus e to the y. But that's nothing like we did over there, is it? This answer doesn't look anything like that answer, does it? Not even a little bit. I mean, I used a black pen over there, I used a blue pen over here. It's kind of obvious, except they're exactly the same, aren't they? Now, which was easier? This one. I just showed you how to do implicit differentiation. There's no problem that I could come up with that would challenge you if all you have to do is take partial derivatives. And so everyone always asks the same question. Why did they show us this in Calc 1? You know, the day after we learned what a derivative is, which is literally when you learn implicit differentiation, because you don't know how to do three-dimensional stuff for quite a while. Yeah, couldn't have shown you this trick in Calc 1, wouldn't have meant anything, but now you have this trick in Calc 3 that this is the way you should always do implicit differentiation. Define a new function and then do partial derivatives. Will you always get the same answer? Yes. And it'll always be significantly easier because there was no chain rule factors, there was nothing complicated. I just got to remember the ultimate result. Now, what about this one? Will it work for multiple variables? Let's try that one. Okay, everybody cool with this? I'm going to erase this because we need the space. Now what I need to do is define a function of 3 variables. So let's let, how about g of x, y, z equal, and the same thing as before. Here's my original equation. That's not a function, it's an equation. You don't differentiate equations. You differentiate functions. So I need a function to differentiate. So I'll just throw this guy on the other side, and we'll call this x squared y squared z plus tan z minus y z squared. This will be my new function. So therefore, the original equation would be a level surface of this. Okay, because I just made it a four-dimensional problem. Now, the question here was to find dz dy. So do you suppose, let's do this. Let's find gy and let's find gz, because those are the two pieces that we're going to need. I don't need the derivative with respect to x, because that's not part of the question. Right? The question was dy. So let's find this. What's that?
2x squared yz.
2x squared y, okay, good. And keep going. Nothing there.
Minus 2yz.
The derivative with respect to y.
Minus z squared.
Just z squared, yeah. Okay, we all good with that? Everybody cool with that? Okay. Now the derivative with respect to z.
X squared y squared.
X squared y squared
Secant squared z.
plus secant squared z
Minus 2.
minus 2yz. Now, the partial of z with respect to y, if we use the same thing we just did a moment ago, I'm asking the question, can we just do the same thing? Well, let's see. That would go on the bottom. And then on the top, I want the negative I want the negative of this on top. So that would be, I'll just take that out. And that would be negative 2x squared yz plus z squared. What do you think? Same thing? Way easier? Yes. Found a really cool trick. And again, the rule is, if I go to a higher dimension, then anything I'm looking at is a slice of something in a higher dimension. That's always true. But differentiating in the higher dimensions is generally easier because everything I can write as functions. I cannot isolate z. That's not possible. So therefore, differentiating z is really, really difficult. But if I make this a slice of something bigger, then it was really simple. So we have you can call it a trick. It's a technique. You can now perform any version of implicit differentiation in any dimension by just simply defining a new function first. Now, there are a few ground rules. You have to define a new function by getting everything on the same side of the equation. That's the first rule of thumb. Okay? And we said, we're defining z as a function of x and y, so I kind of need to pick a new function. You notice I didn't reuse f. That would be a bad idea. A lot of people will do that. They'll just reuse the same function. No, I can't reuse little f because little f is already defined. So I need to make up a new variable. So let's try this out. Let's just see how this works. All right, so suppose we have something like this. I've got, how about, I think it's relatively simple. Got the cosine of x squared y equals, I don't know, y cubed. What if you could isolate the y? What if you could get y by itself? Should we still do this and do it, think of it as an implicit problem, or should we try to differentiate the y by itself? What do you think?
Y by itself.
Probably the y by itself, because you're probably going to get the answer in one step. Everybody understand? If you could isolate the dependent variable, do that, because then you take one derivative and you're done with the problem. So the assumption was I could not isolate the dependent variable. There is no math. I'll have people try to do it. Well, let me just take the cube root of both sides. That's not isolating the y. That's making it more complicated. Taking the cube root of both sides does not make this problem easier. It makes it way worse. Because I still don't have the y by itself. It's because I have y in two places. I can't get it alone. I don't worry about it. So we will define a new function. I like using caps just so I don't confuse it with anything I have before. Does it matter which way I subtract? Why not? Because if I subtract in an opposite order, then I'm changing the sign of both of these simultaneously, which does not change the sign of the final answer, because the final answer is a quotient. So it never matters. The rule of thumb I have, I just typically take everything on the right and move it to the left. That's what I do. I'm a creature of habit. And more often than not, when you have a lot of stuff, you generally aren't going to have more stuff on the right. You might have less stuff on the right or the same amount of stuff, but I usually move everything to the left just because to me, my brain works that way. It's just easier. So I am inclined to go this way, but it does not matter if you go the other way. Okay, so this is the first step of the problem. Now, don't be in a hurry. We have to take two derivatives completely separate from each other and then analyze our result. So I have to find fx and I have to find fy. This is one of the reasons we like this notation. It's very clear. I'm taking the partial of my newfound function with respect to x. I like that notation because there's no way that I can confuse this. Now, don't write this. I see this as a bad habit. All people, well, you know, I'll just write it like this. That's not even a similar quantity. F of x is a function of x. The subscript means it's the derivative of the same function of x. They cannot be the same. That would be impossible. Yeah, this could not equal this, period. So, yeah, don't use that notation. This means the partial of f with respect to x, not f of x. We say f sub x when we're saying it out loud. So what is this one?
Negative sine x squared y.
So negative sine x squared y down the derivative with respect to x.
X squared.
With respect to x,
2xy.
2xy, good. What about this term? 0, yeah. Nothing there. There's no x's, so that piece is done. Now, do I want to clean this up? Sure. But I can clean it up now or just clean it up when I write my final answer. It doesn't really matter. Okay? Does it matter which side the x and y are on? Can I leave the x and y where it is? Yeah. Can I leave the 2 where it is? No. All calculus students do, but it's actually a wrong answer. A coefficient cannot be anywhere except front. That's an absolute. That's an unchanging, unbending rule you learned as babies in math. Yet people will still write x2 rather than 2x. Like, no, a coefficient has to be in front. It's multiplied by the function. The function is not in front of the coefficient, ever. That's basically like misspelling a word and hoping everybody, corrects it for you. Yeah, you have to move the 2 in front. We probably move the xy in front because it's a readability thing. It doesn't matter, but most of us would agree it reads easier if the xy is in front. Now, fy, well, it's going to be the exact same thing to start.
Times x squared.
That's awful looking. And now derivative with respect to y would be x squared
Minus 3y squared.
minus 3y squared. Good. So, the derivative of y with respect to x is. Now, whether you put the negative in front of the quotient bar, or you distribute it into the numerator, or you distribute it into the denominator, all things are correct. But what a lot of folks do is they get really careless about right now, and I'll show you what I mean. Okay, which one goes on top?
F sub x.
Yeah. The first mistake a lot of us make is we don't get that. So that one goes on top. Well, actually, let me put the stuff in front. You said so negative 2xy sine of x squared y. That goes on the bottom. Negative x squared sine of x squared y minus 3y squared. Now, I can put the negative on top and distribute it, or on bottom, not both, because if you put it both, then you multiply by 1, or I can put it in front. It does not matter. I've got every single term is negative right now, so somebody might say, it might be easier to read if I distribute. It doesn't matter. But here. Now, let me ask you a question. Is that the same thing? Sorry, I need to write. This is one of the universal errors that all Calc 3 students make because they get kind of sloppy. I want the negative of this. Is that the negative of this? No. Do you know the number one error, I think, in all of mathematics in the history of the world is always the same thing? Bad distributing of a negative sign. When you have a negative quantity, what's the universal error we make? We only change the sign of the first term because we forget there are parentheses required. Me putting a negative here, it only applies to the first term. It cannot apply. If I said negative x plus y, that is not negative x minus y. There's no distributing of a negative there. I'm only putting a negative in front of the first term. But if I do this, now it's this. Agreed? So if you're going to put a negative here, then you better put parentheses because it's not the same. And if I had to evaluate this at a number, I'm going to get the wrong number if I'm careless with my parentheses. Calc 3 students tend to be very careless with their parentheses. They'll put the negative in front of the first term and the first term only. So either put it in front of the quotient bar or distribute it into one of the quantities. It actually doesn't make any difference. It's not going to change your final answer. So a lot of you will say, you know what, I'm just going to go like this to be safe. Does that seem kind of silly to you to do that? I have the negative of the negative. If you're going to do that, just make numerator positive. You go, oh yeah, there's only one term. Could I put it on the bottom and make both those positive? Sure. Yeah. This is the answer. Okay, I would be inclined to just do this, personally. But, you know, you can do that. Can I improve upon this answer? Are there any common factors on top and bottom?
X.
Problem is no one
Sine
here.
x squared y.
Yeah. This is the answer. Could I make this answer actually smaller? Yeah, I could. By multiplying numerator and denominator by what? Cosecant. If I multiply numerator and denominator by cosecant of this term will be gone, and this term will be gone. And I'll have a cosecant here. In other words, I'll have less stuff. Is that an improvement? Maybe, maybe not. There are times, particularly when you have trig functions in your answers and you have trig functions in your denominators, there are times when multiplying by its reciprocal can make the entire answer smaller. But a lot of you would say, you know what, I'd still rather work with the sine function on top and bottom than work with a cosecant on the bottom. It's the same answer. But I want to remind you that's possible because you're checking your answer in another source, and the answer in the other source is different from yours. So, of course, that means you're wrong, right? Or is it possible there's more than one representation? Yeah, a common error that we make as math students is we assume when we check an answer and it's different from ours, we always assume that we're wrong. No, you know what I always assume? I always assume I'm right. Not that the book is wrong. No, I just assume that's a different form of the same answer. And then I try to manipulate it and see if I can get there. How many have ever used Wolfram alpha? I love using it to check. It's really terrible if you're trying to use it to integrate. Never use it to integrate. It's one of the most powerful software on planet Earth, but it's not well written for the integration. So I tell my Calc 2 students when they're doing methods of integration, I say, do your integrations, don't check the integral on Wolfram because it'll always be different than your answer. Always. Absolutely every time it'll be different than your answer. No, have it differentiate your answer quickly. Because we know the only way to check an antiderivative is by differentiating it. But if that antiderivative was really long and complicated, it was an integration by parts problem, right? Really long, I don't want to differentiate that by hand. It's so long. So what I do is I'll use Wolfram to differentiate it, and do I get back the original integrand? If I did, my answer has to be correct. If I don't, then I've got an error and I figure it out. But what I found with Wolfram, I'll be doing complicated problems. In my Calc 2, I created a table of integrals. All textbooks have one, but they usually only have about 30 integrals. But it says there's 100. No, most of them are actually incorrect. Incorrect, yeah. They give you the answer to the integral as being a more complicated integral. They give you, in other words, a recursion, which is utterly worthless. You can't tell me the answer to an integral is another integral that is more complicated than the one I started with. Because then the answer to that one is another integral that's more complicated, and it's an infinite loop. You can never get an answer. Your answer has to be a closed form, meaning I have an actual function, not another integral. So if the answer to the integral question is another integral, it's a really bad answer. If you look in the back of your calc book, the majority of all your integrals will be more integrals. And some of them are actually incorrect answers. So I created one years ago, and every couple of years I'll add a couple to it. But, you know, all the different forms. So I have over 100 that I've done by hand. But as they get more complicated, you know, I have to check them. So I'll use Wolfram, but sometimes I'll use Wolfram for the integral. So if you're looking at my table, you'll see a quotient. It's busy, there's a lot of stuff, there'll be one quotient. I'll check it on Wolfram, and the rule of thumb is there's going to be at least 7 answers. 4 of them are going to be complex. Even though I integrated a real function, most of the answers will actually be complex. And it might be a sum of 4 different quotients. And then when I put those 4 together and simplify them, I'll get my answer. But the Wolfram answer is never the simple answer. It's always really, really complicated and not simplified. And I always laugh at the fact that I get more complex answers than I get real answers, even though it was a really simple question. It's not wrong, but it's not always useful. So I use Wolfram to check by differentiating, not by doing the same integral, because I'm always going to get a different answer. Okay? So a lot of times you'll get an answer and you'll go, wow, that doesn't look anything like mine, but it might be the same thing. So I always say, can you manipulate it? For example, you got a single term and there's multiple terms, but maybe they're trig terms. Oh, so if I do a little bit of manipulation. So there's a problem that I do where I actually get one simple trig term, and the Wolfram answer is a really complicated quotient with lots of cosecants and cotangents, all of our favorite function. And there's just no way you can see getting from one to the other, but if you manipulate it long enough, you can. But it is so nasty, the algebra. Okay, so I don't try to do that. I'll just take the derivative of my answer and say, did I get back the original integrand? If I did, then my answer is correct. It's a Calc 2 problem that I do. If you were in my class, it was the evil trig. You remember the evil trigs? That was the, okay, there's a typical type of substitution that's really obscure, but it's the only way to do a certain type of problem, and it does, you don't run into a lot. It's anytime you have a quotient where you have trig terms in the quotient, but there's no trig identities that can be employed, you actually do a different form of substitution. It's gnarly. But it allows you to get an answer, and usually the answers are really simple, but if you use technology, the technology answer is almost always really complicated when it doesn't need to be. So we've got this, put this in your back pocket, this is a technique. That's all it is. Now, the next thing we want to do, I want to talk about slope in 3D. Now we mentioned slope is a 2-dimensional thing, okay? I mean, in baby algebra, we call it rise over run. Although I always laugh at that term because no one actually knows what that means. Everybody says rise over run, but then they don't do the right algebra because they don't understand what is, you know, what is run? It's a very, very archaic term that nobody uses anymore. Do you know what the term run means when you say rise over run? Does it have to do with running? No. The term run means horizontal distance. It doesn't have anything to do with run. I'll give you an example. You have a big piece of property and you have a long fence, and you say the fence runs from here to here. And every morning I go out and look and I see the fence running, right? No, a movie played at the theater, and you look at accounts that the movie ran for 30 consecutive days. What does that mean? If you had a calendar that was horizontal, you would say the horizontal distance from the first date to the last date, and that would be the measurement. The term run means horizontal distance that is being measured. It doesn't mean verb run. And nobody uses that term in everyday language anymore. So the run of a film or the run of your fence is a distance. A horizontal distance. That's what the term rise over run refers to. I just say change of y or change of x. But we're in 3D now. Wouldn't we think vertical as being z? That's kind of tricky. So we're going to go hiking at Cowles Mountain. I love using that example because if you've ever been there, you understand this concept. So when you're climbing Cowles Mountain, are you a person who always looks for the less challenging route on the way up or the most challenging route? I don't know. It depends how long your legs are. Because it could be terrible. So I'm standing in a particular place on Cowles Mountain. And if I go in this direction, man, that is really steep. But if I turn slightly, oh, it's not nearly as steep. If I turn here, it's going to be horizontal, so maybe I'll climb this way for a little while. If I turn the other way, now it's a steep descent. So if you said, well, what's the slope where you're standing? My answer would be, it depends. There's 360 degrees I could turn. And at every single turn, the infinitely many directions I could be facing, every one of them would have a different slope, wouldn't it? But the slope would be measured as a slice of the world. So imagine I'm slicing Cowles Mountain, and what you see now is the rim of my slice. You see the level curve. Everybody with me? You see a two-dimensional curve. So now you can think x, y. That's totally okay. And I say, what's the slope of the tangent line of that two-dimensional curve where I am standing? Oh, that's a partial derivative. That's easy. Yeah, it's easy if I'm facing this way or I'm facing this way, but what if I'm facing this way? If I'm facing not along the xz plane or yz plane, but across, well then basically it would be a linear combination of that direction and that direction. So I have, right, I have my slope in that direction, I have my slope in that direction, but I'm asking you to go this way. So it would be a linear combination of those two. Kind of like what we did for the unit tangent and unit normal. We took linear combinations to describe acceleration. We're going to take linear combinations to describe the three-dimensional slope. Okay, and it's actually not difficult at all. So I need to define a few things. Okay, and if you look at the videos, I go through this and I explain things. Now everybody knows that there's calculus in everything you've ever done. I mean, I used the garbage scene in the first Star Wars movie when in the garbage pit and the walls are closing. That's how I actually proved the fundamental theorem of calculus. I used that example. Right? As the walls are closing, you're becoming one with the wall. That's literally how the fundamental theorem of calculus is proved. And everyone knows the cat in the hat, right, Dr. Seuss? Well, that's your first introduction to, of course, three-dimensional calculus. Because what are thing one and thing two? Your two independent variables. I mean, everybody knows that, except little kids aren't really that good at calculus yet, so we just call them thing one and thing two. See, now we call them x1 and x2. We're way better. Could we have an x3 and still do the problem? Sure. Yeah. So, everybody remembers the movie Cars? Come on, you guys were all at the right age. You remember Cars. All right. Who's Lightning McQueen's best friend? Mater. And how is Mater, how does he introduce himself? It's like, come on, I know you know the answer. It's like tomato without the "t," right? Mater is tomato without the "t." Everybody laughs at it. No, that's actually, he was a Calc 3 instructor before he became a tow truck, I think. All right? What is this symbol? That's the Greek letter delta. This is Mater. This symbol, I'm not joking, it's actually called delta without the "t." It's a tribute to Mater. I don't know who came first, Mater or this symbol, but this symbol is called, therefore, what?
Del.
Del. How do you remember it? It's delta without the "t." You think I'm joking? No, that's actually where it comes from. I'm pretty sure that the whole point of the movie Cars was to introduce you to about what we're about to do, slopes in 3 dimensions and things like that. Right? We just introduce it slowly to little kids. This is called the del operator. This creates vectors from things. It's kind of crazy. Here's what we do. Okay, there's two forms of the del operator. We can do the del operator in 2 dimensions or in 3. In either case, we do the same thing. So the del operator, you write it like this. Or it's a vector of operators. It does not equal anything. It is applied to a function to create a vector. So if I have a function, I have some function, to keep it simple, I have some z equals f of x, y. Then the del operator acting on f of x, y becomes that's how it works. The del operator is applied to the function. And so I do the del operator partial with respect to x on the first term, partial with respect to y on the second term. Or I should say on the second term is the partial with respect to y, sorry. Okay? This quantity right here is called the gradient. The gradient is the vector of partial derivatives created by the del operator. Now, a lot of people have heard the word gradient, but it's very doubtful that you've ever actually used one in your entire life. So if you've heard the word used, it was probably used in the wrong context. That's all a gradient is. It's a vector of partial derivatives that was created from a function. There was no vector to start the problem. You created the vector. Kind of crazy. So let's do a simple example. All right, f of xy equals x cubed cos y minus xy squared. Now, you can say gradient of xy, or you can just say gradient of f. It's implied that it's of that function. So it really doesn't matter. But one of the reasons you actually want to say of xy is what you're usually going to do with the gradient vector is you're going to evaluate it at some point. You're going to evaluate some ordered pair. Oh, so then I'd have the gradient of f of 3 comma 7 or something like that. So it's good form. If you left off the xy, it's understood that you're talking about xy, but because you're going to evaluate it, you would have to put the numbers here. So what would this be? Well, the partial with respect to x, you get this, and then the partial with respect to y, tight in here. That. That's it. Okay? Not that exciting. It's what we use it for that's important. Now, if I said, what's the gradient evaluated at a particular point in space? Now it gives me a very specific vector, and that vector has everything to do with slope. Okay? But the problem is, wait a minute. Okay. Let's take something simple like our circular parabola, our bloomin' onion, okay? And I want to talk about the gradient of the bloomin' onion. This one's pretty easy to work with, okay? So this is just 2x comma 2y. Now, I can ask the gradient at an infinite number of points. So let's just suppose on my bloomin' onion, I want the gradient at, let's say, let's use the point, how about 3 comma 4. All right? So what does that look like? Now, I have a point. 3 comma 4 would be about here. But it's going to touch a point on my surface, isn't it? Okay, so first of all, what is f of 3 comma 4? F of 3 comma 4. 25. 25, yeah. Pretty complicated stuff there. So that means there's a point on my surface, 3 comma 4 comma 25. There's a point, and that's where it projected up to. I don't know what to do with that point yet. We're going to learn over the next couple days how the gradient is affected. But the gradient vector, at 3 comma 4, that's what I really want. What would that be then? That'd be 6 comma 8. So there's a vector 6 comma 8, in this case it'd probably be like that, that's coming out of the origin, it's on the floor, or maybe it's coming out of this point. We'll figure all that stuff out over time. Now, there's a vector. I'm on the outside of my bloomin' onion. Okay? So as my bloomin' onion's going this way, if I continue to go this way, it's pretty steep, isn't it? What if I turn around and go this way? I'd have a negative slope. Is it possible I could go sideways on the outside of my bloomin' onion and keep my slope at 0? So if I said, what's the slope on the outside of my paraboloid? You'd say, well, it depends. What direction are you talking about? So I need to give you a direction. Okay? So let's say we have some vector A All right? Vector A is a direction. This would be a two-dimensional. So think of the floor. When I am on Cowles Mountain or I'm on my Bloomin' Onion, if I say what's the slope in a particular direction, I'd be talking about the floor. I want to go in that direction, that direction, that direction. Okay, so if I go in that direction, maybe it's this steep. But if I go in this direction, maybe it's this steep. If I go in this direction, maybe it's this steep. The direction is two-dimensional. Because the direction's on the plane if I choose that direction. So now when I do my slice in 3D and I'm looking at the rim of my curve, because I picked the direction, that's where the slice came from. Now I can talk about tangent lines. So I say go in this direction. Now the problem is that direction could be infinitely long, and I said I wanted a linear combination of these. If my direction was entirely on the xz plane, then all I would need to do is take the partial with respect to x, and I'm done. If it was entirely on the yz plane, then I would just take the partial with respect to y, and I'm done. That would be the equivalent, by the way. Let me make sure you understand this. If I only wanted my answer to be the 2x, remember, slope is not a vector, slope is a scalar. If I only wanted my answer to be the 2x, I'm just saying in general, not just the 6a, but just in general. If I wanted this, the easiest way to do this would be to dot it with 1, 0. That would give me entirely in that direction, wouldn't it? If I wanted it entirely on the yz plane, then I just dot this with 0, 1. So I want it to be at an angle, maybe 45 degrees, I don't know. I want it at an angle. So doesn't it make sense that I should use some of both? How much of both? This is a unit vector. This is a unit vector. So the rule is if I say go in this direction, you make this a unit vector. So if I take my gradient, this is the general. And I dot it with, I'm going to just call it U for unit vector. I dot it with the unit vector. Now that unit vector could be along this axis, it could be along this axis, it could be anywhere in between, it could even be in that direction. Agreed? I'm going to take a linear combination, but I need it to be a unit vector, otherwise my direction is contributing to the size of the answer. Oh, the direction can't. So if I say in this direction, you said 1, 0 because I don't want to change the size of this value. So I do the dot product in the unit direction, and this quantity, this scalar, is called the directional derivative. And it's a very simple notion. So when I do my slice on Cowles Mountain, I say, what's the slope in this direction? You'd say, well, okay, how much in the x, how much in the y? Let me make it a unit vector, and I'll dot it with my gradient, and that will give me an answer. So what if that dot product produced 0? What would that mean?
That direction is 0 gradient.
That you're moving horizontally. Yeah, I'm on the outside of Cowles Mountain, and anybody ever hike Cowles Mountain? I use that example. A lot of people have. It's a nice little hill in Poway? Somewhere not right here. It's a 1,000-foot climb in a really short period of time, so there are very many steep parts to it, and you can enter a lot of different places. But I can move horizontally on the surface of Cowles Mountain. I want to find a safer path, perhaps. I can move horizontally. That's what it would mean. If your directional derivative is 0, you're literally moving horizontally. On the outside of my paraboloid, are there directions I can go that will move me horizontally? Yes. I mean, there's only one direction probably, but I can still get a dot product of 0. Remember, in this case, dot product is referring to the slope. Okay, the two-dimensional slope. So a slope of 0 means you're moving horizontally. So let's go back to our Bloomin' Onion example here. Okay? Find the directional derivative of f of xy equals this at 3, 4, I told you where I want it, but I haven't told you what direction I want. So I'll say in the direction how about in that direction? Okay, so now I'm on the surface of my bloomin' onion. I went 2, 4, so I want to go in this direction. So when I slice my bloomin' onion, you see a curve. Very specifically in this direction, 2, 2, 4. Okay, so right there, now I'm going to go up to this point, right, on the surface of my bloomin' onion. But remember, there's an infinite number of directions I can go. I want to go in this direction. So all I got to do is take this vector here and then dot it with this vector. So what vector do I dot it with in English? The unit vector in this direction. Everybody cool? See, if I said 2,000, 4,000, that doesn't change my direction, does it? But it changes the size of the numbers. Oh, and the size of the numbers can't change my answer. What if I said 0.2, 0.4? I mean, any multiple of this is still this direction, but the problem with that is if it's not a unit vector, I'm using the size of the vector. Remember we always said before, the unit vector takes size out of it. So if I said I want you to go that way's infinite. Oh, go that way 100 feet, so we make that way a unit vector, and then multiply that vector by 100. That's how we got around the size of the vector. So I need the unit vector in this direction. Let's call this vector A. So therefore, first thing is, what's the magnitude of A? So it would be 4 plus 16 under the root, which would be 2 root 5. So therefore, what's my unit vector? You probably did this in your head. 2 over 2 root 5. And then, is this a unit vector? Yeah, you quick check, square, square. So my final answer would be what? 6 plus 16, so 22 over root 5? That would be the slope of the tangent line. If I slice the curve and I go up to that point in space, that's the slope of the tangent line. That's the slope in the direction I'm going. Now, could I get a negative slope on my bloomin' onion? Okay, we're on the outside of the bloomin' onion and we were moving in this direction, so clearly I'm going up. Tell me how we could get a negative slope. What if we go in that direction? Oh, let's make this the opposite sign. If I make this the opposite sign, what's that going to do to my final answer? It's going to make it negative. Now, if you think about it logically, no matter where you are on Cowles Mountain, if I found the direction that was going to give me the steepest ascent, right now that's going to be the steepest tangent line, then doesn't it have to be true if I turn 180 degrees, that'll be the steepest descent at the same time? Can't all of a sudden change. I'm going uphill in both directions? I don't think so. Right? Your parents did that. We know that, right? They walked uphill in the snow, barefoot. You know, I always loved that one, you know, in Southern California, you know, barefoot in the snow. Probably not a lot of that going on, you know. But anyway, so it makes perfect sense. So if I give you a direction that gives you a negative slope, that just means you're going downhill. Could you give me a direction that would have me moving horizontally? This is my gradient vector. That's the thing I'm dotting with. Could you give me a direction that would have me moving horizontally? Don't even think unit vector yet. Just give me a direction. Give me a vector that would have me moving horizontally. Anybody come up with one quickly?
8, -6.
If I make my vector 8, -6, do you all agree that any multiple of that dotted with that would give me 0? Oh, so it's not very hard to find the direction that would give me a 0 dot product. In 2 dimensions, all you got to do is just switch the order and change one of the signs. In 3D, it's a little trickier, by the way. Right? But right now, for our purposes, we only need a 2-dimensional gradient because we're talking about moving on the XY plane the direction, then we move up. So three-dimensional gradients exist, but we don't need those yet. Okay? Now, question. I'm at a particular point on my surface. Let's assume there's an infinite number of points on the surface. Every point on the xy plane, let's keep it simple. Every point on the xy plane is fair game. My domain's the whole xy plane. I got some surface. There's no parts of Cowles Mountain that are black holes or fissures that you'd fall into a infinite crater or something. I can pick any point on the xy plane and project it up. But then there's an infinite number of directions I could go everything is fair game. So at any point on Cowles Mountain, when I find my gradient vector, what direction will maximize my directional derivative? In other words, what would be the steepest? Let's think about this for a moment. I want to keep this really simple. Okay, so you made your unit vector. So let's say you created unit vector u, okay? So now you're going to take your gradient vector that you've evaluated at some particular point. Let's be generic. This is now a vector of scalars. The question is, what direction of u will maximize this? So I want to dot it with u and get the maximum amount. Now this is actually not complicated. This is as easy as calculus gets. Because think about dot product in terms of magnitudes. Isn't this equal to the magnitude of the the magnitude of the gradient times the magnitude of u, oh gosh, what's the magnitude of u? 1, okay. Times the cosine of the angle between them. Well, this is 1. By the way, no matter what direction you're going in, does everyone agree that this is the answer? Oh, so if theta were 90 degrees, you guys just did that a moment ago. If theta were 90 degrees, then my dot product would be 0, wouldn't it? And that's how I move horizontally. And when I asked you for a direction, you guys said -8.6. That was a perfect answer. You picked a direction that gave me a dot product of 0. But I want this to be the biggest it can possibly be, which means I'm not maximizing this. This is a constant. I'm not maximizing this. This is 1. I'm really maximizing this. What value of theta maximizes the cosine of theta?
0.
0. So what direction should I travel to maximize my direction derivative? The direction of your gradient. Sounds strange, because the gradient wasn't the direction you were moving. The direction of your gradient, I'm going to show you what the gradient actually looks like physically next day. But if I move in the direction of my gradient vector was this. So if I move in this direction, that will maximize my directional derivative. If I move orthogonal to that direction, I'll get 0. Then what would minimize my directional derivative? What would give me the largest negative value? 180 degrees. So the negative of my, whatever maximizes it. Now, so that's all I got to do is pick u to be this. Okay, if I want to maximize my directional derivative, then I'm going to pick u to be the unit vector in the direction of my original gradient.
I was like working on grading, and then I was like, oh no! Thank you.
Do y'all agree? So let's see what we get. So let's actually do the dot product now. So if I do the dot product, remember I said, generally speaking, you're not going to do gradients of functions, you're going to do gradients of constants. Okay, because I'm saying at this point on the surface, I want numbers, I don't want functions. It's too complicated, and it's not useful, right? It's actually specific values. What's the slope there, there, there? So I want to dot this with that. So what am I dotting it with? I'm dotting it with this. This looks kind of busy, but it's actually quite simple when I'm all done. And then, whoops. Right there it is. technically, this is the partial with respect, right? Evaluated, blah, blah, blah. I'm going to leave it in that form. It's just less writing. Now, this is a scalar, isn't it? So can I pull it all the way out? And what does that give me? Gradient dotted with gradient. In terms of magnitudes, a vector dotted with itself. In general, in general, v dot v is always equal to what?
Squared.
You all agree with that? We know that. We've used that many, many times. Oh, I have gradient dotted with gradient. That's magnitude squared divided by magnitude. So what's the answer? Just magnitude. So if I said, what is the maximum value of a directional derivative? It's just the magnitude of the gradient. What direction does it? The direction of the gradient. That gradient is kind of useful. So if I wanted to maximize this directional derivative, I would go in this direction, and then the maximum would be simply the magnitude of this. Wow, that's kind of simple, isn't it? That's it. All right, let's do another problem, because this just isn't that bad. All right, let's consider f of x, y is, I don't want it to be too complicated. I'll say xy squared plus, I don't know, 4x squared. Kind of simple. All right, we want to find the directional derivative. Derivative, okay. At, let me just pick a point at random. Let's say negative 2, 4 in the direction so let's say we're going to start at some point hold on. Okay. The notation we use is this: d subscript u negative 2, 4. That's actually the physical notation we use to indicate that I'm taking the gradient vector, dotting it with the unit vector, and getting the scalar answer. Big D for directional derivative in the direction of d. Now, I haven't given you a u. So I've got a point. I'm going from this point to this point. That tells you the direction we're moving. And now I want you to find the directional derivative at this point. That's what I did here. And not at some other random point. So I'm starting at point P, I'm moving towards a point Q. So I told you everything except the direction, but can you tell me the direction? Yeah, what's PQ?
6, 4.
So PQ is, yeah, 6, 4, which would go in the right direction. Now, I haven't taken any derivatives yet. I got to do some work, but none of it's going to be very hard, is it? Okay, so off to the side, let's find our gradient vector. So the gradient of f, again, it's the vector of partial derivatives. Just go slow. This part should never be challenging. Okay, so what is this vector? Y squared plus, I think that's an x squared. Sorry, it's an ugly 2, I know. So 8x, comma, 2xy, yes. I don't want it to be too complicated. Everybody cool with that? I need to evaluate this where? Here. It is not wrong to proceed with functions all the way through and then evaluate at the end, but you've seen before that that just makes things more complicated. I'm far more likely to make errors if I start doing dot products with this versus dot products with scalars. Right? A vector of scalars is a lot easier to work with, and we're done with the calculus, by the way. There's no more derivatives to take. So this is the time I should evaluate this. -2, 4. What do we get? We get 0. -16. Okay. By the way, you notice that I'm putting the vector symbol over this. That is the proper notation. The vector goes over the del, not only that, because it's the vector of that function. So we put the vector symbol over the del, but not over the f. Okay. Now what? I need a unit vector. We found PQ. Now we need to find the magnitude of PQ. And what will that be? So 36 plus 16 under the root. So 2 root 13. So therefore, what is my unit vector? My unit vector will be this over this, so 3 over root 13, comma, 2 over root 13. Always do a quick check. 3 squared plus 2 squared is 13. Okay, good. Didn't mess it up. One step left. What is it? Now I want to actually physically do the dot product. So the way we write it is the directional derivative evaluated at -2, 4 in the direction of u is 0, -16 dotted with 3 over root 13, comma, 2 over root 13. And that would be, what, -32 over root 13. Okay? So we've done every piece of the puzzle. There's nothing else we have to do. The process, it's not difficult. It just really is not difficult. So what did you just say, though? This is the important part. You guys can all give me an answer really simply. But what did you say? I have a surface. Now, we are in 3D. Think of it, let's keep it simple. Z is a function of x, y is kind of the universal thing we're doing. So I have some surface in 3 dimensions. There's an infinite number of points on that surface. I find a point on that surface, I can calculate a gradient vector. There's an infinite number of directions I can travel. What I'm saying is if I slice my surface in the direction of the direction I'm traveling, not the direction of the gradient vector. I'm going to show you next day what the gradient vector looks like on the surface. Before you even pick a direction to travel, the gradient vector, when applied to the surface, shows me something, okay, that's unrelated to this. So I'm on the surface, I have this gradient vector, think of it still on the xy plane. Now I pick a direction. What I'm finding is the slope of the tangent line of the level curve at that point, because I made it a 2-dimensional curve. And when I think of it that way, it's okay to think about it xy. But before was xy, yeah, but now that I've got this curve, I'm standing there looking at the curve. I have horizontal and I have vertical movement. Slope of a tangent line is a fairly simple notion now. If I do a 3-dimensional thing, that's not slope of a tangent line anymore. We can still find the directional derivative. That's still a value, but it won't be slope of a tangent line if my gradient is 3-dimensional. Everybody okay with that? It's only slope of a tangent line if my gradient is 2-dimensional. So I have something, I have a 4-dimensional thing, a function of 3 variables, and I create the gradient vector, and I do all of this process. It's the same process. I do all of this stuff, I'm going to get an answer, but that answer is not slope. It's still a derivative. Now go back when you first learned what a derivative was. Okay, and in my calc class, that's literally lecture 3 or 4 of the whole semester. We first do it, what do? We have a curve on the xy plane, and we figure out how to find the slope of a tangent line. And we use limits, and we find the slope of a tangent line of a function on the xy plane. That's our first introduction to derivative, right? There was a physical picture, we looked at a tangent line slope, and it was really easy to understand. How often have you used a derivative to calculate the slope of the tangent line since? Probably not very many times. Why? Because it doesn't have anything to do with the slope of the tangent line. That's our first introduction. Derivative is just the instantaneous rate of change of the dependent variable per independent variable. It can represent a lot of things, right? It can represent speed. There doesn't have to be a graph associated with it. It's just an instantaneous rate of change now. And I can do it in any dimension. But our first introduction, what was your first introduction to an integral? Wasn't to find the area under a curve? And we did all that stuff. Okay, but integrals are way beyond just areas. Heck, you use them for volumes and surface areas and arc lengths in addition. But now that we know what it is, our first introduction is not the only thing. It's just the easiest one to understand, and then we moved on from there. So if I said the directional derivative is this, it's only slope if I'm here. If I'm in a higher dimension, it's something else, because slope is two-dimensional. There's no such thing as three-dimensional slope. Okay, but I can still talk about derivatives. So let's do a higher problem, just to see how it works. All right.
I'll use the same sort of notation. Now we'll have f of x, y, z, and let's say that's going to be, how about e to the x minus 3y squared, and let's do plus, how about cosine z?
I'll make this really easy.
Now what we want to do is, let's find how about 0, -2, pi, in the direction of a equals, let's say,
Okay. Do we have everything we need? Okay. No part of this should be terribly challenging, but now we got a whole bunch of steps we got to do. So the order of things, I probably want to find my gradient first, and then I want to evaluate my gradient second. That's probably a good way to do things. Okay? All right, what do we get?
E to the x, -6y, negative sine z.
Okay, everybody cool with that?
now let's take our gradient and evaluate it at the point.
Because in actuality, although we can use that, we'd prefer to use the vector of constants, because we're going to do a dot product at some point. It just makes our life easier. So, e to the 0.
1.
-6 times -2,
12.
and negative sine of pi. Okay. In the last example, I started at point P, ended at point Q, and you had to figure out the direction. Now I gave you a direction. Doesn't matter. If I give you 2 points, it takes you, what, 5 seconds to figure out the direction. That's not something that you should be challenged. But a lot of times that's the way the question is asked. That's why I showed you both, just so you don't get troubled over that. I told you the direction, that makes it easy, but I need a unit vector. So I still have to find the magnitude of A. So that'd be what? 36 plus 36 plus 16. What is that?
2 times root 22.
2 root 22.
Yes.
It is always a good idea to reduce, just because it makes your numbers smaller, and you might get canceling. If you don't reduce, it's not wrong, but you're gonna have an answer that may be easier stated. So what is my unit vector? I will state that first. So it's gonna be 3 over root 22, comma, negative 3 over root 22, comma, negative 2 over root 22, and I'll do a quick check. 9 plus 9 plus 4 is 22. Okay, good. Didn't mess it up. So, the directional derivative in the direction of u, I don't need to restate u, I've already got u, evaluated at 0, negative 2 pi, is the dot product of this and this. Okay? And what does that come out to be exactly? It will be 3 over root 22 minus 36 over root 22, I'll put plus 0. Because the third guy was 0. All right, this is the answer. So far, what have we got? We've got negative 33 over 22. Can that be approved upon? This is one of those gray areas. I can leave it alone, but can it be reduced? Yeah. Do 33 and 22 have any common factors? 11. It can be reduced. Okay. What would it reduce to?
3 root 11, or 3 root 22.
I think that's what, right?
Yeah.
That's a better answer because it's smaller numbers. Now, the root 22 didn't go anywhere. There's nothing wrong with this answer, but it might be more useful. Now, does the actual value, the numerical value, if I convert that as a decimal, does that mean anything to me yet? No, it's not 0. It's negative. That probably means something. I'll give you a hint. We're going to use that with tangent planes. When we find tangent planes to surfaces, these numbers are going to help us. Okay, we don't know what they're for quite yet, but they are going to be very, very useful. So today, all about taking derivatives, but nothing hard. And you're going to find the Calc 3 derivatives, most people really enjoy this because you got pretty good derivatives in Calc 1, didn't do a lot of derivatives in Calc 2, concentrated on integration. But in Calc 3, derivatives are a main theme, but you're not learning any new formulas. You learned every formula there exists in the first half of Calc 1. Now what you're doing is you're just using them in different contexts, and now it's all about application. We're going to start talking about surfaces and finding maxes and mins, things like that. We're going to talk about, well, what about optimization, which is considered the most important application in Calc 1. We're going to do optimization in here, but with multiple variables. It's really cool because the level of problem we can attack is beyond what we thought we could do because, again, using partial derivatives to help us answer questions. It's kind of neat. So we are doing derivatives for a little while longer. And then we start integrating, I'll tell you when, 2 weeks from today. So this is week 7. So the first half of the course will end, and that will end our use and application of derivative. Then we'll get into integrals for a little while, and then the vector calculus. And the integration, the introduction to integration, 2 weeks from today is the last material that will go towards the second exam. Okay, so the second exam is going to be primarily, derivatives and applications of that. Any questions? Okay, let's go ahead and call it and do the